Great. So welcome everyone to another week's intercontinental seminar on gravity and cosmology. This week we have the pleasure to have with us Theodore Papanikolaou. Theodore got his PhD in Paris with Vincent Venin, which is not the French accent, of course, but yeah, in 2021, if I remember correctly. And then he was a postdoc in Athens, and now he's in Scuola Superiore Meridionale in Napoli, in my alma mater, where I did my PhD. And today he's going to talk about primordial black holes and induced gravitational waves. So thanks a lot, Theodore. The floor is yours.
Thank you very much, Kostas, for the invitation. So as you can see for the title, we will discuss today primordial black holes and induced gravitational waves, which were one of the major topics of my research during the last 5 years. So let me start with a brief introduction on primordial black holes formation mechanisms. So from now on, I will call them PBHs for using an abbreviation. So traditionally, black holes were considered to form due to the collapse of enhanced cosmological perturbations in the early universe before star formation. This mechanism can be easily realized within ultra-short roll inflationary setups, as well as during early matter-dominated eras, where we have a linear growth of energy density contrasts of matter perturbations with no radiation pressure. We also have a formation mechanism of these objects related to the collapse of cosmic strings, as well as to collapse of domain walls. And in the recent years, we also have a formation mechanism of PBHs related to collapse through bubble collisions during a cosmological phase transition in the early universe. In the following of the talk, I will focus mainly on the first formation mechanism, which is the most studied one. So to understand these more in detail, we actually consider that each objects, these black holes, are formed whenever we have enhanced cosmological perturbations, which basically we need to require that the energy density contrast of the collapsing ever density region becomes greater than a critical threshold value, which in general depends on the equation of state of the universe at the time of PBH formation. This basically happens when the typical size of the overdensity which collapse re-enters the cosmological horizon. Here, with this schematic figure, we see the evolution of the cosmological horizon scale as a function of time, here in terms of e-folds. And we see in the gray dotted line, the evolution of a large-scale mode, typically brought by CMB and LSS experiments, which re-enters the horizon later in the late matter-dominated era, where in these large CMB scales, we have strong constraints from Planck for a scale-invariant power spectrum. However, if we go to smaller scales, which exit the horizon nearly the end of inflation and re-enters back right after its end, for these scales, we don't have current observational constraints, strong ones. So potentially in these scales, we can have a peak in the power spectrum, which can collapse and form a primordial black hole. Now, a crucial question to ask is why we should study these objects, why it is interesting. So to answer this question, we should take into account what is the mass of these objects. And the mass of these objects basically is of the order of the cosmological horizon mass whenever we have the collapse. So after some Siebel algebra, we can find that the mass of these black holes scales inversely proportional with a Hubble parameter. So this gives us an opportunity to probe a wide range of masses, as we can see here in this schematic figure, which is related with a very rich phenomenology. In particular, with very small mass black holes forming at the end of inflation, we can probe the physics of the early universe. And then as time passes, we can potentially form more massive black holes. Typically, black holes with 10 to 9 grams, which are quite light, evaporate around Big Bang nucleosynthesis time, so they can play a role there through their evaporation in the abundance of the light elements produced during this epoch, while 10 to 15 grams mass PBHs evaporate today. Then at later times, around the QCD phase transition, we can have the production of fun solar mass black holes, which are the typically order of masses detected by LIGO Virgo experiments. And then later at BBN, we can have the production of supermassive black holes, of the order of million solar masses, which are the typical masses of supermassive black holes residing in the galactic centers. Very interestingly, in the asteroid mass window here, up to now, we don't have strong constraints or even no constraints on the abundances of primordial black holes. So there are recent arguments saying that in this mass window, potentially, primordial black holes can constitute up to the totality of the dark matter. So having said that, as a motivation behind primordial black hole physics, let me also make a brief discussion regarding the observational status of the field. So to do so, we need actually to set some constraints, observational constraints, on the abundances of the black holes. And typically, we discriminate between two types of constraints depending on when these black holes evaporate. So here I show you the evaporation time of a typical Schwarzschild black hole, which scales cubically with its mass. So for black holes with masses less than 10 to 15 grams, we have evaporation which has been completed by now. So the observational constraints we can put on the abundances of these black holes come basically by studying the effects of the products of Hawking evaporation on the abundances of light elements produced during BBN, on the spectral shape of CMB, and as well as on the galactic and extragalactic cosmic ray background. For higher masses black holes, which are still, have not evaporated yet, we can put constraints on their abundances by studying gravitational lacing effects, dynamical effects of these objects on an astrophysical system, accretion, effects on large-scale structure formation, as well as their gravitational wave counterparts. Here, I define a new quantity, which is the ratio between the abundance of the black holes today over the abundance of dark matter. Showing you in this figure the abundances, the constraints on this quantity as a function of the mass of the black holes. On small mass, in the small mass region, as I said before, we have constraints which come basically by studying the effects of PBHs evaporation. Whereas in the higher mass scales, we have constraints from lensing here, from CMB, from gravitational wave, from accretion. Here I list all the the probes, observational probes we have now, which puts constraints, on these objects. Interestingly enough, in this asteroid mass window, we don't have constraints. So in these mass range, black holes potentially can constitute up to the totality of the dark matter. So having said that, regarding the observational status of the field, let me move now by connecting primordial black holes with gravitational waves, which will be the main part of the talk. So a first channel to connect PBHs with GWs is the portal of primordial induced gravitational waves, which are produced due to second-order gravitational interactions. In particular, if we go to the cubic order, a gravitational Lagrangian, we will see a coupling between the first-order scalar perturbations of the metric phi with the tensor perturbations h. So whenever phi is enhanced and leads to the collapse of a black hole, through this coupling, it can induce at the same time tensor modes, which are translated to gravitational waves. We also have gravitational waves which are associated with the Hawking radiated gravitons emitted out of the process of Hawking evaporation. But these gravitational waves typically peak on very high frequencies and currently are not reachable with current gravitational wave observatories, or at least also future ones like LISA or Einstein telescope. We also have gravitational waves which are associated to mergers of primordial black holes. Finally, I need to mention a fourth channel, which is also induced gravitational waves at second order, like the first one, but this channel is induced by number density fluctuations of primordial black holes themselves, and not by the primordial scalar metric perturbations phi we saw in the first channel. This last gravitational wave signal was introduced first by my collaborators and me during my PhD 5 years ago, and we saw that it can be abundantly produced during an early matter-dominated era driven by light primordial black holes. So having said that, before going to the main part of the talk, let me focus more on induced gravitational waves and give some generic context. So to understand induced gravitational waves, we should bear in mind that their nature is nonlinear inherently, and this is comes from the fact that the field equation of the equations of the gravitational field are structurally nonlinear if we go beyond first order in cosmological perturbation theory. So lower order metric perturbations can act as source of higher order metric perturbations. This was realized already in late 90s, in the beginning of second millennia, where people started to study scalar-induced gravitational waves. So gravitational waves which are induced by scalar metric perturbations. Here I mentioned some indicative literature regarding research on the induced gravitational wave field. So we see here some first works by Ananda Bowman in 2007 on scalar-induced gravitational waves. We also have some recent works on tensor-induced scalar perturbations. We have induced gravitational waves from scalar tensor mixing. We have also vector perturbations induced by scalars, and also tensor-induced tensor perturbations. So as you can see, there is a very active the field of induced gravitational waves is very hot during the recent years, especially after the discovery of gravitational waves. So let me now then focus on scalar-induced gravitational waves, which is the most studied one in the literature. So to study scalar-induced gravitational waves, we actually need to perturb our metric. Here I do it in the Newtonian gates by considering the first-order scalar perturbation, usually called Bardeen gravitational potential, introducing the second-order tensor mode in the metric Hij we can see here. One then, by minimizing the cubic order gravitational Lagrangian, they can extract the equation of motion for the secondary tensor modes H, we can see here, which are now are sourced by source term S, which can be recast as quadratically dependent on the first order scalar perturbations, as you can see here, phi phi. So it's indeed a second order quantity. Then one can define the gravitational wave spectral abundance as the energy density contribution of gravitational waves per logarithmic comoving scale, which can be recast at the end as proportional to the tensor power spectrum. With this being obtained after a long but straightforward algebra as a convolution integral of the power spectrum of the first order scalar perturbations phi. This kernel function f here, I don't give the full expression because it's quite complicated, contains information on the equation of state of the universe at the time of gravitational wave production. We can also write a similar formula in terms of the power spectrum of the comoving curvature perturbations, which is what is typically probed by cosmological probes, by exploiting the relation between r and phi on superhorizon scales we see here. Let us then focus on ultralight primordial black holes, which was my main field of research in the last 5 years. But before presenting you some results of my work, we should bear in mind that the abundance of the black holes, of these primordial black holes forming in a radiation background, scales linearly with the scale factor, since black holes behave effectively as pressureless dust. And this is quite important, since due to this growth of their abundance, if we start with a relatively initially high enough initial abundance of these black holes, we can arrive at the later time with abundances of the order of unity. So we can have early matter dominated eras driven by primordial black holes. This is the case for black holes with masses less than 10 to 9 grams, which evaporate before Big Bang nucleosynthesis. These black holes can trigger early matter-dominated eras with a very rich phenomenology. In particular, through the process of Hawking evaporation of these ultralight black holes, we can reheat the universe and produce democratically all the standard model particles we know. We can also potentially alleviate the Hubble tension, since due to the process of Hawking evaporation, we can produce also in the primordial plasma dark radiation degrees of freedoms, which can increase an effective and potentially the Hubble parameter at early times. We can also produce naturally the baryon asymmetry through CP violating out of equilibrium decays of Hawking radiated degrees of freedom. And finally, we can also induce gravitational waves, scalar induced ones, but which are induced by PBHs number density fluctuations, which can be detectable by GW detectors, as we will see in the following, and according to some recent works here, can be in good agreement with the recently released PTA GW data in the nanohertz frequency range. So having said that, let's go now to the main part of the talk. So initially, we will discuss gravitational waves, which are induced by PBH number density fluctuations. Imagine then that we have a population of primordial black holes which are randomly distributed in space and which, for simplicity, they all have the same mass. So we consider monochromatic PBH mass function. So under these assumptions, one can extract the PBH matter power spectrum, which can be recast in this form, being dependent on the PBH mean separation scale, rho bar. The appearance of this scale makes us introduce a natural effective UV cutoff scale associated with this mean separation scale, below which we start to probe the granularity of the PBH matter field entering the nonlinear regime, where P becomes greater than unity and where perturbation theory breaks down. Since then, we have a two-fluid system. We have radiation, which collapses and forms black holes, which acts as pressureless dust. We can define an isocurvature perturbation in this way, accounting then for the fact that black holes initially at their formation time are subdominant compared to radiation, and also taking into account the conservation of energy, we can find that the isocurvature perturbation at formation time is almost equal to the energy density perturbation of the black holes, and which in itself is proportional to the number density fluctuation of these objects. One then can see the number density fluctuations of PBHs as an isocurvature perturbation. This isocurvature perturbation, when later black holes will dominate the energy budget of the universe, will convert to a curvature perturbation associated with its gravitational potential phi. One then, by treating carefully super and subhorizon scales, can extract an analytic expression for the power spectrum of this PBH gravitational potential, which can be recast in this form. Here we see clearly the appearance of the UV cutoff scale associated to the PBH mean separation scale. We also have the KD scale, which crosses the horizon at the onset of the PBH domination era. And also we have the KEVAP scale, which is the scale crossing the horizon at the end of the PBH evaporation. This scale enters in this suppression factor as phi, which is present here due to non-zero radiation pressure, which is dominant for modes with time variation larger than the PBH's evaporation time. Having then this power spectrum for phi, we can compute the induced gravitational wave signal, entering it into the convolution integral for the tensor power spectrum I showed you in the beginning. We also, before showing the signal, however, I need to comment on the frequencies probed by this portal, which depend on the mass of the black hole shown in the color bar and their initial abundance. And as you can see, it can span a wide range of frequencies, which can be probed by Einstein telescope, LISA, and square kilometer arrays. Here in the right panel, we show the signal by counting, as I already mentioned, for the convolution integral of our power spectrum of the PBH gravitational potential, and which as we can see, it peaks, it has a quite peaky behavior around the UV cutoff scale, which is something expected if one accounts from the fact that the transition between the early matter-dominated era, when black holes evaporate, to the late radiation era is quite sudden if we consider monochromatic mass functions as we did in this case. More physically, one should identify, to understand this peaky behavior, the dominant source term of the induced gravitational waves. And for our case, it's this term which is proportional to the derivative of the gravitational potential square. And what is how phi behaves during the transition, in particular during the MD era, phi is constant. So we start with a phi prime which is 0, which goes to something non-zero during the late radiation domination era. So due to this term, one gets a resonant enhancement of the gravitational waves around the UV cutoff scale. So up to now, we studied gravitational waves which are induced by a population of black holes which are randomly distributed in space. This is the case for typical Gaussian curvature perturbations which collapse and form black holes, and which leads to a Poisson clustering of the population of these primordial black holes. Let's now relax this assumption and consider the case of a cluster PBH population due to the presence of primordial non-Gaussianities. For our case, we will focus mainly on local type non-Gaussianities, which are actually described with the nonlinear parameters FNL, GNL, and tau NL, which actually quantify the relative strength of the bispectrum and trispectrum, so of the 3-point and 4-point correlation function of the curvature perturbation with respect to the power spectrum, PR. Then, using a path integral formalism, one can compute any correlation function of the PBH matter field. In particular, we are interested to the 2-point correlation function of the PBH matter field we see here, which is related to the PBH matter power spectrum. Then, focusing on superhorizon scales and smoothing our energy density field of primordial black holes on scales smaller than the typical PBH characteristic scale at formation, we can recast the PBH matter power spectrum after a long calculation as a sum of the Poisson term, which is k cubed, as we saw before, plus another term, which is proportional to the primordial curvature power spectrum itself, times some quantity which depends on the trispectrum parameter tau NL. So because this expression is quite complicated, we introduce here an effective tau NL, which is this double integral over momenta of tau NL times our window function, our smoothing function of the density field, times the primordial curvature power spectrum. So having done that, we can write in a simpler form the power spectrum for PBH curvature perturbation, which is a sum of the Poisson term plus the clustering term we just saw. Let us now see how this this power spectrum for phi scales with k by making some assumptions regarding our underlying primordial curvature power spectrum and our tau NL nonlinear trispectrum parameter. So the first instance we do for the primordial curvature power spectrum is that we consider as nearly scale invariant curvature power spectrum on CMB scales as imposed by Planck, and a log normal peaked power spectrum on smaller scales with an amplitude of the order of 10 to minus 2, which is the typical amplitude necessary for black holes to collapse. Then we make a secondary ansatz regarding our tau NL inspired by a scale-dependent FNL parameter by parameterizing a tau NL as a log normal, again, distribution peaked at the PBH formation scale. So having done that, we can fix our free parameters at hand, which is MPBH, omega PBH, and compute tau NL bar from the integral I showed you before, and plot here P phi over K. Interestingly, on small scales, we are dominated by the Poisson noise with P phi scaling as K minus 5 over 3, whereas on large scales, we are dominated by the non-Gaussian clustering term. Here, K critical is the scale below which we transition between the two regimes, basically. Here, I need also to make a comment on the hierarchy of scales, of the relevant scales at hand. And we need to mention that for the range of values for the mass of the black holes we consider and their initial abundance, all of them are, their comoving scale are above 10 to 5 inverse megaparsec. So we indeed probe very small scales, which are currently inaccessible by CMB and large-scale structure experiments. Having then our power spectrum for phi, we can import it in our usual formula and extract the induced gravitational wave signal. So we see here in the dotted red line our numerical result, and also we managed to find an analytical approximation for this gravitational wave signal I show you here in the green line. What we observe is that on high frequency, So on small scales, we are dominated by the peaky Poisson gravitational wave contribution I presented in the beginning. But on lower frequencies, we have the appearance of a secondary peak, which depends on the trispectrum parameter tau and L. In particular, its amplitude depends on the joint product of tau and L times PR, the primordial curvature power spectrum. We exploited this fact in order to set some upper bound constraints on these joint parameter tau and L bar and PR on very small scales by saturating the gravitational wave amplitude on the upper bound we have for primordial gravitational waves from BBN. So by doing so, we see here the upper bound constraints on tau and L bar times PR as a function of the mass of the black holes and their initial abundance. We plot these upper bound constraint in the color bar axis here as a function of the mass of the black holes and the initial abundance. Here, these strange regions, here and here, the cutted gray ones, comes from the fact that we also take into account some upper bound constraints we have for gravitational waves, for stochastic gravitational waves from the LVK collaboration. So the parameter space was even more reduced because we have now some data as well from gravitational waves. The gray regions are excluded since there we have overproduction of gravitational waves, the upper gray region, but the lower gray region is actually out of interest since there we don't have a PBHs dominated era. So having said that, up to now we studied scalar-induced gravitational waves, which are induced by PBH number density fluctuations, accounting as well for the effect of local type non-Gaussianities on PBH clustering. So let us now move in another topic, which is related to induced gravitational waves, but now we will see induced gravitational waves induced by vector metric perturbations, not by scalar ones we already discussed. So this is the case of gravitational waves induced by vector perturbations, which are sourced by primordial magnetic fields. And this is related to a recent paper of us, which was released last April, which you can see here. So let me introduce first the vector perturbations in the metric through these two vectors, zeta I and psi z, which actually, due to a gauge redundancy, reduced to just one vector perturbation variable, Vi. Then, by minimizing again the cubic order, the gravitational action, we can extract the equation of motion for the first order vector perturbations, which can be recast in this form. In the absence of an external source, these modes generically decay, and this is why people neglect them in the literature. However, if we have an external source which have a vector type source, this source can actually sustain vector perturbations. This is the case, as we will see in the following, for primordial magnetic fields, which can act as a source of vector metric perturbations. So before going to the technical details of our calculation, let me give a bit of context on primordial magnetism. According to observational evidence, we know that our universe is weakly magnetized on galactic scales of the order of 10 kiloparsec, with the magnetic field measured at these scales of the order of micro-Gauss. This micro-Gauss magnetic field can be explained actually through astrophysical dynamo mechanisms, which can amplify a primordial seed up to these values. However, if we go to intergalactic scales, which are of the order of 1 megaparsec, these dynamo mechanisms face some challenges. And what we know up to now is just some lower and upper bounds on this intergalactic magnetic field of the order of 10 to minus 16, the lower bound, and the 10 to minus 11 Gauss, the upper one, which are related due to non-observation of secondary GeV cascades from TV blazars and due to CMB and 21 centimeter observables regarding the upper bound. So a legitimate assumption to do is to consider a primordial origin of magnetic fields on intergalactic scales. So doing so, one needs to introduce the two-point function of these magnetic fields, which is fully characterized by the magnetic power spectrum PB introduced here. We can also define usually standardly a stress energy tensor associated to this PMF and extract the vectorial part of this stress energy tensor through the use of the projection tensor BIN here. So at the end, we will have the equation of motion for our vector-metric perturbations, which are sourced, as you can see here, by the vector magnetic anisotropic stress PVI. This equation can be solved analytically and with the solution taking this form, and which, as you can see, VI is proportional to the magnetic anisotropic stress and has a time dependence which crucially depends on the equation of state of the background. In particular, we saw that if we have stiffer and stiffer equation of states, we have a decay of the vector modes which is slower and slower. And in the extreme case where we have kination, so W equal 1, we have a constant vector mode, so we have a sustained vector metric perturbations which can induce gravitational waves, as we will see in the following. So let's recapitulate. We have our external source, which is a primordial magnetic field, which sources first-order vector modes, and these vector modes can induce secondary tensor modes translated to gravitational waves. So at the end, by minimizing again the cubic order gravitational action, as we did for the scalar-induced gravitational waves, we extract here the wave equation for the secondary tensor modes, which are now sourced by source term being dependent on vector metric perturbations, as you can see clearly here. For convenience, we work in the Fourier space and we decompose our tensor modes with respect to the helicity basis. So at the end, the source term is this complicated expression, but what we should take in as a home mission is that is indeed quadratically dependent on the vector metric perturbations, like in the scalar case now. So having said that, we can proceed and compute the tensor power spectrum, which is related to the two-point correlation function of the tensor modes. This two-point correlation function is proportional to the two-point function of the source term times some green functions which actually can be regarded as the propagator of the tensor fields of the tensor mode, being the solution of the homogeneous tensor wave equation. These green functions are actually functions of and be expressed in terms of Bessel functions and depends crucially on the equation of state of the universe at the time of gravitational wave production. Then we took into account that our source now depends on our vector modes. So at the end, one needs to compute a 4-point correlation function of the vector perturbations, which is proportional to the 4-point correlator of the magnetic anisotropic stress we introduced before. However, using the Wick theorem, we were able to decompose this 4-point correlator function to a product of a 2-point correlator of the magnetic anisotropic stress. In order now to extract some qualitative results, we made an assumption, and by modeling our primordial magnetic field power spectrum, which is the source of the vector modes, and at the end the gravitational waves, by modeling it as a power law, which is motivated by many primordial magnetogenesis model, and is characterized by its amplitude and its spectral index NB. Then one can compute the magnetic anisotropic stress square we saw before as a convolution integral of this magnetic power spectrum. In order, however, to have a microphysical realization of our magnetogenesis, a seed of our primordial magnetic fields existing in the early universe, we consider a particular model, which is the Ratra model, where the primordial magnetic fields are generated due to the breaking of the conformal invariance of the Maxwell action. So here we have this extra term in the electromagnetic action, when we can see here the non-conformal term here, depending which is actually characterized by this non-conformal indexed S. One at the end can relate the parameters of our phenomenological magnetic power spectrum, the amplitude and the spectral index, as a function of the non-conformal coupling S and the energy scale at the end of inflation H-in. This A-inf is the scale factor at the end of inflation, which can be expressed in terms of H inflation, the duration of the post-inflationary era in E-folds, delta N reheating, and the post-inflationary equation of state W reheating. At the end, we are left with 4 free parameters of our physical setup, which is the energy scale at the end of inflation, delta N reheating, the non-conformal coupling, and W. So let us go on and compute our gravitational wave signal. Doing so, I remind you again that this gravitational wave spectral abundance is proportional to the tensor power spectrum, which itself is related to the two-point correlation function of the tensor modes. At the end, we can compute the gravitational wave spectral abundance today from the gravitational wave spectral abundance at the end of the post-inflationary era, so at reheating, multiplying it by a dilution factor which accounts for the expansion of the universe. Here we need to stress that we have a characteristic scale in our problem at hand, since we consider only modes which crosses the cosmological horizon during the post-inflationary era. So we study gravitational waves induced by vector modes which are actually generated, which cross the horizon during the post-inflationary era. In this way, our characteristic scale at hand is K reheating, which is the scale crossing the horizon at the end of the post-inflationary era, which depends on our free parameters, H inflation, W reheating, and delta N reheating. Before compute now the gravitational wave signal, I need to mention, to be honest, some approximations we did in order to keep our calculations analytically tractable. So the most crucial issue we need to mention is MHD turbulence, which is expected to be dominant in the post-reheating era, and which requires the performance of MHD simulations, which are highly costly. So in order to avoid these, we consider only gravitational wave, vector-induced gravitational waves taking place during the post-inflation era. So in this way, we underestimate our gravitational wave signal. This is why we run our time integrals from eta inflation up to eta reheating, and the momentum integral from k inflation up to k reheating. So at the end, we have an accurate estimate of VIGW produced at the onset of the radiation domination era on sub-horizon scales. Regarding super-horizon scales, we made an approximation by using the universal IR scaling, which scales as k cube, and which is valid for well-behaved source terms of bilinear form, which happens to be the case of our primordial magnetic fields. This was the case also in the case of scalar-induced gravitational waves, which present a universal IR scaling of k cubed in the very small comoving scale region. However, we should be careful and not to trust this k-cube approximation if we go close to k reheating from below. So there, we expect to have a loss of accuracy regarding the spectral shape of our gravitational waves. However, in the high K region, so on small scales, where we have an accurate estimation of the VIGW, we managed to get a detectably large signal for a realistic choice of our parameter space, for the values of our free parameters at hand. So let me go now to the results. So here in the left panel, we see how our VIGW signal scales with frequency by fixing delta and reheating and by varying H inflation. We see in the left dotted part of the spectrum this k-cube scaling I mentioned, which should not be trusted, whereas in the solid in the right region here, where we have an accurate estimate, here the result, it's trustable. And the general trend is that if we increase H inflation, we increase the amplitude of the GW signal and increase the frequency to the right. Then here we fix H inflation and vary delta and reheating. And the trend is that if we increase delta and reheating, we increase the amplitude again, but we decrease the frequency. This increasing of the amplitude is somehow expected, since for higher delta and reheating and H inflation, we have a longer post-inflationary era during which we produce these vector-induced gravitational waves. Here I should remind you that the peak frequency of our gravitational waves is related with K reheating we introduced before and depends in this way on our free parameters H inflation, W reheating, and delta reheating. Here we vary both H inflation and delta and reheating by keeping a constant the gravitational wave amplitude. And here it's a useful plot where we show how our peak frequency scales with H inflation and delta and reheating for the case of kination, where we have the maximum enhancement of our vector modes, and which, as you can see, it can lie within a wide range of frequencies from 10 to minus 10 up to 10 to 12 hertz. So it can be potentially detectable by future current gravitational wave detectors. Then let's move on and also make a comment on how our amplitude of gravitational waves at the peak frequency scales with our free parameters, which is H inflation and delta and reheating. By making a numerical investigation, we found that omega GW at the peak frequency follows a power law with respect to H inflation and an exponential one with respect to delta and reheating. So by summarizing, this is our final scale relation of the peak GW amplitude as a function of our free parameters. Now let me conclude. So today we saw that primordial black holes are associated with a very rich phenomenology depending on their mass, and in particular within the asteroid mass window, where we do not have observational constraints on their abundance, these objects can constitute up to the totality of the dark matter. We also study the portal of gravitational waves induced by PBHs, number density fluctuations, and by vector metric perturbations, showing that induced gravitational waves can serve as a probe of the early universe, in particular of the small-scale curvature power spectrum, on primordial non-Gaussianities, and on primordial magnetogenesis models. So that was all I wanted to mention, and I want to thank you for your attention.
Thank you very, very much, Theodore, for the very nice talk. Are there any questions from the audience? Yeah, I don't see anyone, so I'll try to clarify some things I might have missed. So discussing scalar-induced gravitational waves, I think you used both the Bartin potentials to be equal, right? So that there was supposed to be no anisotropic stress there, or is this
Yes.
simplification, or why is that?
Yeah, because in ZR, I mean, in the early universe, you don't have, I mean, the presence of an anisotropic stress. I mean,
Okay.
mm.
And that was my second question. How tied is this the whole analysis to lambda CDM, let's say? And like, are there any studies in like modified gravities or like,
Yes,
yeah?
yes, yes. We actually, in some follow-up papers, we studied together with my collaborators, with Manos Aridakis, Spiros Vasilakos, and Harry Jerefos, and also Salvatore Capocciello, this gravitational wave signal within f of r gravity theories, where we have the presence of anisotropic stress, but of geometric origin.
Mm-hmm.
And we saw that actually, depending on which f of r gravity you consider, this stress can play a role or not. For example, in Starobinsky gravity, r square gravity, this anisotropic stress of geometric origin is negligible, so it's like GR. But if you have a Rn, so a power law of r gravity, then it plays a role, and it can act as a source of gravitational waves, which we studied in our case. So it will change the spectral shape of this gravitational wave signal. Yeah.
Mm-hmm. Nice. Yeah. Any other questions? What about higher order? Do you think that they're going to be even less, let's say, I don't know, so the frequency will be lower, even lower, or it will be even less detectable, less possible to detect? Like
You mean?
tertiary, if you go to higher order. So I guess you get the induced gravitational waves because at first order, of course, you don't have any coupling between the modes, while at second order there is coupling
Yeah.
between. Yeah. So what happens in higher? Like, do you know if anyone studied like higher
Yes,
order?
yes. There are some people from China, the group of Xingzi Zhu, where they studied the third order gravitational wave, so third order tensor modes. And
Mm-hmm.
indeed, they found some detectable signal as well. So they have some different spectral shape. And this is very important in the context of modified gravity, because depending on the gravity theory you have, you will have different couplings between the scalar
Yeah.
metric and vector modes and higher order. So it can be a signature of modified gravity, or you can use it to break the degeneracy. This we comment and we make a discussion in our papers regarding this possibility. Yeah, this is very important.
Nice. Okay, let me stop the recording here. Maybe